This module is called Mathematical Preliminaries Part 2. In this section, we provide a brief introduction to some other notions used in semantics, namely relations and functions. What we do here is we provide definitions of these concepts and then look at different kinds of relations and functions that are of use in different branches of mathematics, with a special focus on their uses in linguistics, especially in semantics. The first is relations. In everyday language, relations are taken to be different kinds of links between objects. Examples of these might be kinship relations like sister of, father of, mother of, is an ancestor of, or topological relations like part of, is a subset of, or simply links like is older or younger than, has the same height as, is taller than, etc. Formally, we define relations between elements of sets. Various conventions are used to describe relations. We often write RAB or ARB for A bears the relation R to B. The standard way of defining binary relations in set theory is as sets of ordered pairs of elements, in which case one may simply say that the ordered pair AB belongs to R to mean that A bears the relation R to B. If uppercase A and uppercase B are any sets, and R is a subset of the Cartesian product of A and B, we call R a binary relation from A to B, or a binary relation between A and B. A relation R in or on A is simply a subset of A squared. We define the terms domain and range of a relation as follows. Dom R, the domain of R, is the set of A's such that the Cartesian product AB is a member of R for some B, that is, the set of first elements of the ordered pairs in R. Range of R is defined as the set of those B's such that the ordered pair AB is a member of R for some A, that is, the set of second elements of the ordered pairs. Consider an example where A equals the set consisting of AB, B equals CDE, and the set theoretic relation R equals the ordered pairs AE, BD, BE. Here, Dom R equals AB, which equals uppercase A, and range R equals DE. Note that if R is a binary relation from A to B, the domain of R is a subset of A, and the range of R is a subset of B. Let us consider some operations on relations. The complement of a relation R between A and B is defined as R apostrophe equals the Cartesian product of A and B minus R. Note that the complement of a relation depends on what universe we are considering. This is because a relation can be a subset of more than one Cartesian product, and its complement will differ according to what Cartesian product we are taking to be the relevant universe. Thus, if R is the relation described in the last paragraph, that is, R equals AE, BD, BE, its complement relative to the universe, the Cartesian product of AB and CDE, will be the following. R apostrophe equals AC, AD, BC. The inverse of a relation R between A and B is defined as the relation R to the power minus 1, a subset of the Cartesian product of B and A, defined as R inverse equals BA, the set of all ordered pairs BA such that AB is in R. it is easy to verify that the inverse of R is R. For the relation R described above, the inverse of R is EA, DB, EB. More examples. Let n be the set of natural numbers 0, 1, 2, 3, 4 ad infinitum. Let R be the relation is less than on n. That is, it's a subset of n squared. Now convince yourself of the following. Those of you who are familiar with mathematical proofs may try to prove these assertions. The complement of R with respect to n squared is the relation is greater than or equal to b. The inverse of R is greater than. There are different kinds of relations that are of interest. Here we take a look at some of these. A relation R on A is said to be reflexive if and only if for all x in A, x are x. A relation R on A is said to be irreflexive if and only if for all x in A, xx is not a member of R, which means x is not related to itself. Examples of reflexive relations include the relation, the set consisting of all ordered pairs AA such that A is a member of A, the relation S defined as the set of ordered pairs XY such that X and Y are in the set of natural numbers and X is less than or equal to Y. Examples of irreflexive relations include R1 equals the set of ordered pairs AB such that AB are both in uppercase A and A is not equal to B, and S1 such that defined as the set of all ordered pairs XY such that XY is in N and X is strictly less than Y. A relation R is said to be symmetric if and only if for all xy in uppercase A, if x are y, then y are x. R is antisymmetric if and only if for all xy in A, if x are y and y are x, then x equals y. R is asymmetric if and only if for all xy in A, if x are y, then it is not true that y are x. The identity relation mentioned above is symmetric. The relation S is antisymmetric. S1 is asymmetric. Note that asymmetric relations are vacuously antisymmetric. They are antisymmetric by definition. Note that an antisymmetric relation is simply an asymmetric relation which possibly contains some ordered pairs where the first member and the second member are identical. A relation R is said to be transitive if and only if for all x, y, and z, if x are y and y are z, then x are z. All the relations mentioned in the last two paragraphs are transitive with the exception of R1. More examples. Let H be the set of humans who live in Delhi. Let S2 be the set of those ordered pairs XY such that XY are members of H and X has the same height as Y. S2 is reflexive because everyone has the same height as themselves. Symmetric because if X has the same height as Y, Y has the same height as X. And transitive because if X has the same height as Y and Y has the same height as Z, then X has the same height as Z. Also, S2 is neither antisymmetric nor asymmetric. Note that in principle a relation can be both symmetric and antisymmetric, but this happens only when R is the empty set, okay, or the empty relation on the empty set. Relations like S2, which are reflexive, symmetric, as well as transitive, are called equivalence relations. An equivalence relation R on an empty set has the interesting property that it partitions the set into jointly exhaustive and mutually exclusive blocks consisting of sets of members of A, such that every member of each block is related by R to every other member of the block, and every member of A that is not in the block is not related to the member of the block mentioned before. Moreover, every member of A is in some block defined by R. Let us introduce some definitions here. Let S be a set. A set, uppercase Greek letter pi, consisting of subsets of A is said to be a partition on S if and only if the following conditions are satisfied. The empty set is a member of pi. For all Si, Sj that are members of pi, if Si is not equal to Sj, then the intersection of Si and Sj equals the empty set. The unary union of pi is the set S. Now suppose R is an equivalence relation of A. Define pi as follows. Pi is the set of all S's, all sets S, such that for some x that's a member of A, S is the set of all y's such that y are x. Work will show that pi as defined here is a partition on A. Since R is reflexive, every x is R related to something, namely to itself, and so each member of pi is non-empty. Reflexivity also guarantees that every member of A is in some member of pi. This is because if A is a member of uppercase A, then A are A, and hence A is a member of the set of y's such that y are A, and the set of y's such that y are A is a member of pi. To see that the members of pi are pairwise disjoint, suppose, contrary to fact, that there are two distinct members of pi, say S and T, which are not disjoint. Since S and T are members of pi, it follows from the definition of pi that for some x, S equals the set of y such that y are x, and for some z, T equals y such that y are z. Since S and T are distinct, either there is an element of A, which is a member of uppercase A, which is in S. In other words, A is a member of S, but A is not a member of T, but not in T, or vice versa. Suppose the former. The case with the latter is exactly parallel, so we don't need to set it out in detail. Then, given the definitions of S and T, it is true that A are X, but not A are Z. Since by assumption S and T are not disjoint, there is a B in A such that B is in S and B is in T. Again, this means that B are X and B are Z. By symmetry, X are B and B are Z, and so by transitivity, A are B. Again, by transitivity, A are Z, which contradicts our assumption that not A are Z. This means that if A and T are distinct, they must be disjoint. All of this may sound rather abstract, but to see what the theorem says, consider the relation S2 described above. We saw that it is reflexive, symmetric, and transitive on the set of humans in Delhi. What the theorem above says is the following. S2 divides up the set of H of humans in Delhi into blocks consisting of humans who have the same height. All humans of Delhi are members of some block, and each block has all and only those humans in Delhi who have the same height. Equivalence relations and this theorem about them are useful not only in various branches of mathematics, but also in formal semantics, in thinking about various phenomena, for example, the semantics of comparative constructions in natural language. And finally, we look at a class of relations called order relations. A relation is called a reflexive pre-order if and only if it is reflexive and transitive. An irreflexive pre-order is irreflexive and transitive. The relation S2 mentioned in the previous paragraphs is a reflexive pre-order. Another reflexive pre-order would be the relation S3 on H, defined as S3 equals the set of all ordered pairs xy such that xy is in H and y is at least as tall as x. S3 is reflexive and transitive, but unlike S2, it is not symmetric, hence not an equivalence relation. At the same time, it isn't antisymmetric either, because if A and B are humans from Delhi who have the same height, then AS3B and BS3A, but A is not equal to B. A relation R is called a reflexive partial order if and only if it's reflexive, antisymmetric, and transitive. An irreflexive partial order is irreflexive and asymmetric and transitive. The relation S, defined before, the set of all xy's such that xy's are natural numbers and x is less than equal to y, is a reflexive partial order, whereas Sy, defined as the set of ordered pairs xy such that x and y are natural numbers and x is strictly less than y, is an irreflexive partial order. Okay. See the reason you want to think about them. Just reflect a little bit on what we said before. Let A be a set, pow A be its power set. The relation subs on power set of A, defined as the set of ordered pairs xy such that x is a member of the power and y is a member of the power set A and x is a subset of y. Subs is reflexive because every set is a subset of itself. It is antisymmetric because if x is a subset of y and y is a subset of x, then x and y have the same members, therefore x and y are identical. Subs is also a transitive relation because if x is a subset of y and y is a subset of z, then x is a subset of z. The proper subset of relation defined similarly will be an irreflexive partial order. A reflexive partial order is, furthermore, a reflexive linear or total order, also sometimes called a chain if it also further satisfies the condition that for all A and B in the relevant set, either A are B or B are A. An irreflexive linear or total order is an irreflexive partial order that further satisfies the condition that for all A and B in the relevant set, if A is not equal to B, then A are B or B are A. The relation S in the last paragraph is a reflexive total order, and S1 is an irreflexive total order. The relation subs, on the other hand, is a reflexive partial order, but it is not a total order since it is possible to have subsets of A where neither is a subset of the other. Examples of the relevant order relations can be found in various branches of mathematics, and in linguistics they are found not only in semantics but also in other domains like in syntax. Thus, syntactic trees are characterized by two fundamental relations on the sets of nodes: dominance and precedence. Dominance is an irreflexive partial order. Precedence, defined on the set of terminal nodes, on the other hand, is an irreflexive linear total order. Functions. We are all familiar with functions from elementary mathematics and algebra. A function is intuitively thought of as a process or a correspondence. In precise set theoretic terms, however, they can be defined more precisely as a special kind of a relation as follows. A relation f from a to b is called a function from a to b if and only if the domain of f equals a and the range of f is a subset of b. Each element of the domain of f is paired with just one element of the range. That is, from AB belongs to f and AC belongs to f, it follows that b equals c. Alternatively, one might just say that a function is a subset of the Cartesian product of a and b such that each element of A occurs as the first element of exactly one ordered pair in R. So consider the sets A defined as AB and B defined as 1, 2, 3. The following relations from A to B are functions from A to B. P, the set consisting of A1 and B1. Q, defined as the set consisting of A2, B3. The following relations from A to B are not functions from A to B. S defined as B3, T defined as A2, B1, B3. S fails condition 1 of the definition, T fails to meet condition 2. S is a function on the smaller domain, the singleton of B. T is not a function at all. The notation F column A arrow B is frequently used in order to say that F is a function from A to B. Elements of the domain of a function are called arguments, and their correspondence in the range, their values. If the ordered pair AB is a member of F, the familiar notation F applied to A equals B is also used. Map, mapping are commonly used as synonyms for function. A function maps each argument into a corresponding value. A function f from a to the power n to a is called an n-ary operation in A. Sometimes partial functions are considered. In this case, the condition 1 in our definition might fail. Some terminology now. Functions from A to B in the general case are said to be into B. If the range of the function equals B, the function f is onto B or a surjection. A function A from A to B is called one-to-one function or injection, just in case no member of B is assigned to more than one member of A. So if A is not equal to B, f of A is not equal to f of B. A function which is both one-to-one and onto is called a one-to-one correspondence or bijection. It is easy to see that if a function is a one-to-one correspondence, then the inverse of f is a function and a one-to-one correspondence. One useful class of functions are characteristic functions of sets. The characteristic function of a set S, considered a subset of some larger domain D, is defined as follows. F subscript S from D to the set consisting of 0 and 1 is that function such that fs of x equals 1 if and only if x is a member of S and is 0 otherwise. That is, x is not a member of S. There is a one-to-one correspondence between sets and their characteristic functions. In semantics, where it is common to follow Frege in viewing much of semantic composition as carried out by function argument application, it is often convenient to work with characteristic functions as functions of sets rather than with sets directly. Characteristic functions are used in many other applications as well. To see these points, consider the following functions mentioned above. From A to B, A is the set consisting of lowercase a, lowercase b, B consisting of 1, 2, 3. We defined P as A1, B1, Q as A2, B3. P is neither 1 to 1. A and B are both mapped to 1, nor onto, because 2 and 3 do not belong to the range of P. Q is 1 to 1, but not onto, because 1 is not a member of the range of Q. Now consider the following function, the squared of function. S4 defined as that function from n to n where each natural number is paired to its square. So S4 equals 0, 0, 1, 1, 2, 4, 3, 9, and so on. S4 is 1 to 1, but not on to n. Since all numbers which are not perfect squares are left out from the range of S4. However, let P1 be the set of perfect squares, that is, the set consisting of 0, 1, 4, 9, 16, 25, and so on, then S4 is both 1 to 1 and onto P1. That is, it's a bijection from n to P1. What is interesting about this is the fact that P1 is a strict subset of n. Note that if A and B are finite sets and have definite cardinalities, it is impossible to have a bijection from A to B or B to A. So if A equals AB and B equals 1, 2, 3, and so the cardinality of A is less than the cardinality of B, any 1-to-1 function from A to B will fail to be onto, and any onto function from B to A will fail to be 1-to-1. Okay? In fact, it's impossible to have a 1-to-1 function from B to A. One corollary of this fact is that if A is finite, it is impossible to have a bijection from A to a proper subset of A. However, we just saw that this is not the case with sets like the set of natural numbers, n, for which you can have a bijection from n to a proper subset. This is because an infinite proper subset still has an unending supply of members that can serve as values for natural numbers in a bijection. Two sets for which there is a bijection from one to the other are called equinumerous sets. We write this as A squiggle B. This fact is used in set theory to define what it means for a set to be infinite. Basically, we have the following definition. A set A is infinite if and only if there is a set B, which is a strict subset of A, which is equinumerous to A. That is, for which there exists a bijection from A to B. This means, whereas it is impossible to extend a finite set in such a way as to preserve its cardinality, an infinite set can be extended or contracted without affecting its cardinality. It turns out, for example, that the set of odd numbers, the set of even numbers, the set of rational numbers, that is, fractions with non-zero determinants, the set of algebraic numbers, numbers that can be solutions to polynomial equations, these will include the rational numbers plus some irrational numbers like the square root of 2, the square root of 3, the cube root of 2, the cube root of 3, and so on. Proofs of some of these assertions can be found in the text mentioned in the references. Now, does this mean that every extension of the set of the natural numbers yields a set equinumerous to n? It turns out that no. The set of real numbers, defined as natural numbers followed by a decimal point followed by an infinite sequence of natural numbers, is not equinumerous with n. More generally, the mathematician Cantor proved that if A is a set and pow A is its power set, then A is not equinumerous with pow A.